Okay, let's see some more interesting examples. So here we are now going to use the property of decomposing signals. So we saw how to decompose any given signal to even and odd part, and we said that they are orthogonal, and then we saw some examples of orthogonality, how to find out if a signals are orthogonal or not. Okay, and then we saw that sinusoids are all orthogonal. Whatever we saw here, all of these are orthogonal. Okay, so real valued sinusoids, they are orthogonal as long as they are of different frequencies. Complex valued sinusoid, once again they are orthogonal as long as they are of different frequencies. Here if you note that the complex valued sinusoid here is of frequency omega, whereas here it is of minus omega. They are two different frequencies. If you are trying to compute omega and plus omega itself, this will go to infinity and hence they will be not orthogonal. So we saw that all sinusoids are orthogonal to one another as long as they are of different frequencies. Now let's try and decompose some example signals into even and odd part. Okay. Something which we learnt just now. So we just saw that this function is not even or odd. So let's decompose that to get even and odd part. This is 0, 1. How do we get the even component? Remember, we have to add this with the time reversed version. Okay, so this is rect of t minus half. The time reversed version that we want is rect of minus t minus half. Okay, so this is where all your skills of shifting in time and scaling in time is going to be helpful. Now we have to scale in time with minus 1, which is basically time reversal of just the reflection here. Okay, now you add these two and take an average. What you get is the odd part. What you get is the even part. So this is the even component. Okay, now how do you get the odd part? You add this signal with the negative of this signal and then take the average. Right, so when you negate this signal, what do you get? Whatever is here moves on this side. Okay, so in other words, we'll get something like this, where this is minus half, this is plus half. Okay, this is the odd. So now we have the odd and even components of rect of t minus half. Now when you add these two, we'll get the original signal back. Okay, let's see another example. So let's see this one, which we already saw earlier was neither even nor odd. Okay, so e power minus t. Now what is the time reversed version of this? This is simply e power minus t when t is negative, which makes this minus of minus t. Okay, this is what you get. So this is the negation of this. In other words, you can say this is e power t for t less than 0. Okay, that's the time reversed version. Now, of course, this value is 1. Now, when you add them up an average, you get something like this, where the peak is half. So basically, what is this? This is nothing but you say that this is the signal even part is equal to e power t when t is less than 0 and e power minus t when t is greater than 0. Of course, there is So when you want to plot the odd part, as simple as that. So there you have half, here you have minus half. So this is the odd part, which is half of minus e power t when t is less than 0, and then plus e power minus t when t is greater than 0. Okay, that's it, as simple as that. Okay, now let's go back to our regular signal that we often encountered. So this also we said is neither even nor odd, right? Let's try and find out its even and odd components. As usual, first step, let's take its mirror image or time reversal. So this is x of minus t. Now let's find their average. If you find their average, then you find out the even part. So what would the average look like? Okay, so this is the average. Peak is of course 1, and these points are half. Okay, so this is the even part, and let's get the odd part. So for odd part we have to subtract, right? So when you subtract one from the other, what do you get? So you get something like this for the right hand side, and the left hand side obviously has to be the reflection. Okay, and what is this value going to be? It is going to be half. This is going to be minus half. So this gives us the odd signal. Okay, now earlier we saw that when we multiplied an even and odd signal, we ended up getting an odd signal. Now what are the other possible combinations that we could have? We can not just multiply, we can also add, right? So when we have such combinations of signals, what happens to these signals? So let's see what happens. So let's call the product of these two signals to be z of t. Now if let's say one of them is odd, the other is even, then what happens to this product? We already saw that it has to be odd. So this we already saw. Now what if both are even? Then it's simple, right? So z of minus t is going to be x of minus t into y of minus t. Both are even, which is going to make them just x of t and y of t, which is z of t itself. So the resultant is also even. Now what if both are odd? Then z of minus t is x of minus t times y of minus t, which is equal to minus of x of t times minus of y of t, which is also equal to z of t itself. So it's still even. So when you have product of two signals where both are even or odd, then the product is even. Only when one of them is odd, you get the product to be odd. Okay. Okay, this is simple and it follows from whatever we discussed earlier. Now, what if we are just adding? Let's see the simple cases first. Let's say that this is equal to again z of t. Now, if z of minus t is what we're trying to compute, then it is once again just change the signs everywhere. Individual signals are all anyway even, so this gives us z of t. So when both are even, you still get even signal. When both are odd, once again you get an odd signal, which is minus z of t. The problem arises when one of them is odd, another one is even. Let's see what happens here. Let us say x is odd. So which means we'll get minus x of t, and y is even, we'll get y of t. So this is not equal to minus z of t or not equal to z of t. And you get some weird signal. So this is neither odd nor even. Of course, you can split it into odd part and even part, but as such, the entire signal, when you add up an odd and even signal, is neither odd nor even. Okay, this once again helps us in our analysis later. So let's take some examples and see what happens. So tan omega t. So is this function odd or even? So because we know what is tan, if we plot the graph, we of course know that this goes to infinity, something like this. This function we know by plotting that it is going to be an odd signal, right? But we can also use these properties and know that because tan theta is nothing but sine theta times 1 by cos theta. Okay. So this is an odd signal, this is an even signal, and the product has to be odd, and hence tan is odd. Okay. Now what about e power j omega t? Is this even or odd? So this is basically nothing but sum of two signals, and those two signals are cos t plus j sine omega t. So this is even and this is odd, okay, which makes this entire signal to be neither even nor odd. Okay, so a complex sinusoid is neither even nor odd. Whereas a real valued sinusoid can be even or odd. If it is cosine, it is even. If it is sine, it is odd. But a complex valued sinusoid is neither of those. Similarly, e power j omega t is also neither even nor odd. But can complex signals exhibit some other kind of symmetry? It is possible that complex signals can exhibit some other kind of symmetry. We'll see next what are the kind of symmetries that complex signals can exhibit.